All right. So yesterday we introduced the notion of Laplace transforms, and today we will see why they are useful in the context of ordinary differential equations. Okay. So I told you yesterday, though I did not actually demonstrate how, that Laplace transforms are a very convenient way of repackaging an ODE in the form of an algebraic equation. So all we have to basically figure out is how to find the Laplace transforms and inverse Laplace transform of certain functions, and then you're good to go. So how does this practically work? So to understand how this practically works, let us start at the beginning and understand how to compute the Laplace transforms of derivatives of functions. So Laplace transform of derivatives. Why are we interested in this? Well, an ordinary differential equation is defined in terms of ddx and d square, dx square, and so on and so forth. So we at least have to understand how to calculate the Laplace transforms if we are to convert an ODE into an algebraic equation. So let's start with a very simple calculation of the Laplace transform of the derivative of a function. So L of f prime. Okay, here by f prime, remember that f is a function of the variable t, right? And the Laplace transform of f is denoted as capital F, which is a function of the variable s. So when I say derivative, I mean df dt. So what is L of f prime? That is the question. Okay, so let us compute it from first principles. Let us plug this in the definition of Laplace transform and calculate what this quantity is. L of f prime equals integral 0 to infinity, weight the function that you want to calculate the transform of by the factor e to the minus st, which is the kernel for the Laplace transformation, f prime dt. Okay, so this can be written, of course, as e to the minus st df, which invites us to use a udv formula. So this is my u and this is my dv, and if I do that, I get, excuse me, this is equal to e to the minus stf evaluated between the limits f and 0 minus integral 0 to infinity okay. So this is the VDU part, integral VDU part. Now, if I evaluate the first quantity at infinity, of course, this is 0 because e to the minus infinity is 0. At 0, it doesn't vanish. It takes the value of whatever the function takes at f at t equal to 0. So this becomes minus f at t equal to 0 plus s times integral e to the minus st f dt. Okay. Now, this integral you recognize as basically the Laplace transform of the function f. That is the definition of this guy. Okay, so I think I've been using script L, so I will stick with that notation. So then all said and done, if you know the Laplace transform of the function, the Laplace transform of the derivative of the function is rather straightforward. You simply have to compute s times the Laplace transform of the function and take off the value of the function at t equal to 0. Okay. Now you see that this is defined with respect to the value of the function at t equal to 0. So this is going to naturally incorporate initial value problems, as we will quickly demonstrate using an example. Okay, before we do that, let us actually calculate the Laplace transform of the second derivative also. Again, start at the beginning. 0 to infinity. This is f double, excuse me. My f turns out to be weird. F double prime dt, right? Again, I will use the udv formula. So I can write this as integral 0 to e to the minus st ddt df dt dt, right? So d of df dt would be my dv. So if I again use the udv formula, I will get e to the minus st df dt evaluated between the limit 0 to infinity minus integral, again, df dt, and then du would be minus s e to the minus st dt. Okay. If I evaluate the limit again, I find this is equal to minus f prime at 0. Okay, at infinity, this vanishes. At 0, it takes the value of the derivative of the function at time t equal to, t equal to 0, whatever the variable t is, plus s. And what's inside the integral, you recognize as the Laplace transform of the first derivative of the function, which we have already evaluated. So let's plug it in. Plus s times this is equal to, from the equation above, s times L of f minus f of 0. Okay, so the Laplace transform of the second derivative of the function is basically s squared times the Laplace transform of the derivative of the function minus s f0 minus f prime 0. Okay, and you can quickly see that you can iteratively continue this process and get the Laplace transform of the nth derivative of a function. Simple enough. The generalization would be, the generalization of this would be the Laplace transform of the nth derivative would be equal to s raised to the power n Laplace transform of the function itself minus s to the n minus 1, the value of the function at 0, minus s to the n minus 2, the value of the first derivative at 0, minus so on and so forth, times minus the n minus 1th derivative evaluated at 0 with no s out front. Okay, so if you plug in n equals 2, you will recover the formula above. Okay, so this is how you calculate the Laplace derivative of functions. Now, before we move on, for completeness sake, I will also tell you how to calculate the Laplace transform of an integral, and you might have to use this to solve certain problems, even though I will not use it in this lecture because I'm going to be solving ODEs, but it's useful to know the Laplace transform of an integral. Okay. So again, let capital F of s denote the LT Laplace transform of a function f of t. Okay. Again, which is piecewise continuous. So maybe I'll just write it, which is piecewise continuous for t greater than 0, the semi-axis t greater than or equal to 0, and satisfies the growth restriction that we discussed yesterday. What was this? This is basically the absolute value of this function should be bounded by some exponential kt so that the Laplace transform doesn't blow up. Okay, so then for s greater than 0 and s greater than k, remember that if s is less than k, the Laplace transform is not guaranteed to exist. And of course, t greater than or equal to 0, the Laplace transform of the integral of this function. So remember that I'm using a slightly different variable inside the integration because after I integrate it out, what remains is some function of t, which is what I want. So the Laplace transform of this integral is basically given by 1 over s times the Laplace transform of the function itself. Okay. Now the proof of this is rather straightforward. I will not spend time on it. You simply have to assume that this integral is some function g of t and calculate the derivative, and this would pop out immediately. Okay. So this is how you calculate the Laplace transform of an integral. For any simple integral of a function that is piecewise continuous, as long as you know the Laplace transform of the function itself, then the Laplace transform of the integral of the function is basically the Laplace transform of the function weighted by 1 over s. Okay, so nothing could be simpler. So for our purposes now, we want to move on to understanding how to use Laplace transforms. So use of Laplace transform in solving initial value problem. Okay, so this is the major thrust of today's lecture. So how will I use the Laplace transform to solve initial value problems without having to go through the homogeneous equation, the general solution, so on and so forth. And these are, of course, watertight methods and ones that you should not forget. But in many cases, the Laplace transform actually makes your problem much, much easier in cases where the inverse of the Laplace transform can be guessed without too much trouble. So before I outline the general methodology, let me quickly work out an example, okay, so that you understand how it works in practice. Example, and then we will talk about how the general methodology works. So suppose I give you an initial value problem. So the problem is y double prime plus 4y prime plus 4y equals some function is t squared e to the minus 2t, okay? Now I make this an initial value problem by claiming that at t equal to 0, y is 0, and at t equal to 0, y prime is also equal to 0, and solve this initial value problem. Now, of course, you guys know how to solve this already. You can use any one of the methods that you know, like undetermined coefficients or variation of parameters, both of which are applicable here because the homogeneous equation is rather simple. So you can figure out a bunch of Wronskians and do the variation of parameters if you want, or since the right hand side is t squared e to the minus 2t, you can probably go the way of undetermined coefficients also, but I think variation of parameters might be easier in this problem. But what is still easier would be using Laplace transforms, as we will demonstrate. The first goal is to take this calculus problem and convert this into an algebraic problem. So again, remember that this goes under the general umbrella of what's called operational calculus. So to do that, I will simply take the Laplace transform of both sides of this equation. So I'll take the Laplace transform of the left-hand side equals the Laplace transform of the right-hand side. Okay. The hope is to convert this into an algebraic equation so that all that remains to be done is to calculate the inverse Laplace transform of some function. So let us look at the left-hand side and right-hand side separately. So left-hand side, again, I will use the linearity property, and I can write this as the Laplace transform of y double prime for 4 times Laplace transform of y prime plus 4 times the Laplace transform of y. Okay. Now, of course, I know the formulas. It's useful to write them down again. This is equal to s square L of y minus s f of 0 and minus f prime of 0, so minus y prime of 0. Okay, so again, I will use the notation that we have developed. Remember that the Laplace transform of a function is denoted by the capital letter of the function itself. So this I will write s square y. Now for this problem, it turns out that y at 0 is 0 and y prime at 0 is also 0. So this is just s square y, right? Now L of y prime is, of course, L of y minus was SL of f minus f of 0. So SL of y minus y of 0. Okay. Again, this is simply for this particular problem, this is just s times y because y at 0 is 0. So put everything together on the left-hand side becomes s squared y plus 4sy plus 4y. Which I can write as s squared plus 4s plus 4 times the Laplace transform of y, which is capital Y, which is a function of s, remember. Now look at the right-hand side. What is the right-hand side? L of t square e to the minus 2t. Now, this is where you need a little bit of familiarity with how to calculate Laplace transforms and inverse Laplace transforms. So first, whenever you see a function weighted by e to the minus 2t, you should always remember the shifting theorem, S shifting theorem that we saw yesterday. S shifting simply tells you that if you know the Laplace transform of a function, then the Laplace transform of e to the at times the function is basically the Laplace transform of the function f with s replaced by s minus a. Okay, so this is the first shifting theorem. So basically what we have on the right hand side is t squared e to the minus 2t. Here a is minus 2. So we simply have to know what is the Laplace transform of t squared. Well, that we know because L of t to the n is n factorial divided by t to the n plus 1. Right? So L of t squared is basically 2 divided by t cubed. Sorry, whatever. So this is not t, but it is s. S to the n plus 1. So this is s cubed. Okay, which tells me that the Laplace transform of t squared e to the minus 2t, I simply have to replace s by s minus a, where a is minus 2. So this is basically 2 over s plus 2 whole cubed. Okay. So now I will write this ODE as an algebraic equation equating the left and the right hand sides of the equation. The left hand side is s squared plus 4s plus 4 times y of s. The right hand side is 2 over s plus 2 whole cubed. Of course, the left hand side is just s plus 2 quantity square. And this is equal to this, which tells me that the Laplace transform of the y that I'm looking for is given by 2 over s plus 2 quantity to the 5th power. Okay. So which means the only thing that remains, the only non-trivial portion of this question is what is y? What is the function whose Laplace transform is 2 over s plus 2 the power 5? In other words, y of t is basically the inverse Laplace transform of y of s, which is L inverse of 2 over s plus 2 to the power 5. So this is the only thing that you have to guess. And this is where some familiarity helps. So you should solve a few problems in Laplace transform so that this becomes second nature for you. So once you can figure this out, the rest is pretty much straightforward. So remember that whenever you have just 1 over s to the something, then there is a t to the power n involved, right? And since I have not just s to the 5, but s plus 2 to the 5, there is some shifting involved. So I can use these two formulas that we just talked about. L of t to the n is n factorial over t to the n plus 1. So I can guess that there is some t to the 4 hiding here, right? Because the Laplace transform of t to the 4 is basically 4 factorial divided by t to the 5, s to the 5. Again, I keep writing s, t, I'm sorry. Should keep writing s, right? Okay. So I know that there is a t to the 4 hiding somewhere up to some numerical factor. But it's not just s to the 5, it is s plus 2 to the 5. So basically this guy has been shifted by a equals minus 2. So I should multiply this function by e to the minus 2t. So I can guess that my y of t is 2 times t to the 4 e to the minus 2t. Right? But if I didn't have this function, I should have a 4 factorial floating around. Since I don't have a 4 factorial floating around, I should divide it by 4 factorial. In other words, all I'm saying is that L of t to the 4 e to the minus 2t is 4 factorial divided by s plus 2 to the 5. Okay. Does this make sense? So if I calculate the inverse Laplace transform of this guy, I basically get t to the 4 e to the minus 2t divided by 4 factorial. So when all is said and done, I know the answer to the problem that I'm looking for. And that is simply, if I divide this out, I get t to the 4 e to the minus 2t divided by 12. Okay, that's pretty much it. So I never had to solve any, remember, this is an inhomogeneous equation that we started with. I never had to solve any homogeneous equations. I never had to solve any Wronskians. I never had to solve any whole bunch of determinants. All I had to remember is what is the Laplace transform of certain elementary functions. Okay. So the Laplace transform technique makes your life really easy when it comes to solving initial value problems, as long as we are not dealing with functions that are extremely complex, so that the Laplace transform cannot be easily guessed. As long as you can guess the Laplace transform, you're golden. Okay, so you can go ahead and solve the problem. So I will sketch the general methodology, and I will also leave you with a problem that you can think on your own. So the general methodology is as follows. Recapitulating what we just discussed. Suppose you're given the initial value problem, y double prime plus ay prime plus by equals some r of t, where r of t, remember, is some input, some driving force or some input to an engineering problem. And they tell you that the value of y at t equal to 0 is some k0, and the value of the derivative at t equal to 0 is some k1. This is a statement of the initial value problem. Your first step is, of course, take the Laplace transform of both sides so that you don't have to deal with all these pesky derivatives. Okay, and the Laplace transform of r of t I will call as some r of s, capital R. So what is this guy? The first term is s square times y minus the value of the derivative at time t at t equal to 0 minus s y at 0. That is the first term, plus a times s y, the Laplace transform of the function y, minus y at t equal to 0, plus b times the Laplace transform of the function y equals capital R of s. Okay. So now collect terms. Remember that y at 0, y prime at 0 are not necessarily 0. So we solved a problem in which they were actually equal to 0, which made our life slightly easier. But even if they are not 0, there'll just be a couple of other terms floating around. So that should not make things too difficult. So collect terms. So you have s square plus as plus b multiplying the Laplace transform of y, and the remaining stuff can be taken over to the right hand side. So I have a y of 0, so an s plus a times y of 0, and I also have plus y prime at 0 plus the Laplace transform of the driving force r, or the input r. Okay, so this equation that you get by these manipulations is called the subsidiary equation. Okay, so all one has to do is now get an equation for capital Y. This is an algebraic equation. I can divide both sides by s square plus as plus b with impunity. So I'll call this q of s. Q of s is a square plus as plus b. So multiplying both sides of this equation with q of s, I get the Laplace transform of the function that I'm looking for is s plus a y of 0 plus y prime of 0 times q plus r of s times q of s. So this is it. Now, once you know what this is, basically all you have to do is take the inverse Laplace transform of both sides, and that will give you y of t. That's pretty much the entire methodology. There is nothing much to it. So something nice happens if y and y prime at t equal to 0 or 0. Suppose if y at 0 equals y prime at 0 equal to 0, the kind of problem that we just worked out, then it turns out that y of s is basically r of s times q of s. Okay, or this tells you that q is y over r. What is y? Y is the Laplace transform of the response, right? Which is what we are looking for. The response is what we are looking for. Response of the system to the external stimulus or the driving force. R is the stimulus or the driving force. So you can think of this as output over the input. So that's why the symbol Q is reserved for this particular ratio, because Q is what you would call an engineering problem as the gain or some other function. Okay. So typically the problem proceeds in 4 steps in solving Laplace ODEs using Laplace transforms. You write down the problem, the given problem, in T space. Okay, so I will put a box around this. Now you convert this into a problem in S space, subsidiary equation. Okay, so write this down in S space. Now from here you form the subsidiary equation and solve the subsidiary equation. So solve the subsidiary equation, and this will give you the inverse Laplace transform, capital Y of S. Okay, and then from here you simply take the inverse Laplace transform and figure out Y of t. Okay, so it's basically a 4-step problem, or rather a 3-step problem, because the problem is given to you. So the only non-trivial aspect is going from this to this, right? Where you have to take the Laplace transform and guess things right. And of course, the last step where you have to take the inverse Laplace transform. But I assure you that if you solve a couple of problems, this will become second nature. So this is written in the T space. And this is written in the S space. Okay. So I will leave you with one thought, the answer to which you can find in your book. Now, all of this assumes the initial conditions are given to you at time t t equal to 0, right? But what if they are not? Suppose the initial conditions, remember that the Laplace equation itself is defined from 0 to infinity. So I don't have any freedom in choosing the Laplace transform of the first derivative and second derivative, right? So this is f of 0 only. It is not f at something else, because the lower limit of the integral is 0. So if the initial condition is also given at t equal to 0, like for example this problem, I can use the methodology straight away. But if it is not, then I need to shift the t in my integral correctly. So suppose if the IVP is such that you are given, let us say y at some initial time, t0 and y prime at t0. Okay, then to do the problem, when you take the Laplace transform, you shift the t. So you basically say t goes to some t tilde plus t0. Okay, so what happens now? Well, you're given the initial values with respect to t. With respect to t, of course, the initial values are at t equal to t0 and and y prime at t equals t0. But with respect to t tilde is t minus t0. So at t equals t0, t tilde is 0. So with respect to the shifted variables, now you can convert the initial value problem into something that has y at t tilde equal to 0 and y prime at t tilde equal to 0. Okay, so this with simple shifting, you can again use the same formulas that we have developed. So I encourage you to look at example 6 in the textbook. Okay, that exemplifies this method. And then solve exercise 15. Okay, So if there is any questions about any of this, you can ask me in the next class, but these are relatively straightforward. Okay. So any questions or any comments about any of the things that we have talked about thus far? Okay, so I'm going to start one problem, but I will stop it quickly because I want you guys to think about this. So we'll solve another example problem. Okay, and again, this is basically an exercise in understanding Laplace transforms and inverse Laplace transforms. It's not really about ODEs at all. So I'll give you a slightly more complicated one to think about. So the question is y double prime plus 2y prime plus 5y is 10, 10 cosine t. Okay. Now I'm also telling you that at t equal to 0, y is 0, and at t equal to 0, y prime is 3. So how will you go ahead and solve this? So first, again, we should form the subsidiary equation. To form the subsidiary equation, you have to take the Laplace transform on both sides. So the Laplace transform of y double prime plus 2y prime plus 5y is s squared times the Laplace transform of y minus s times, y at 0 minus y prime at 0. That is the first term. The second term is 2 times the Laplace transform of y prime, which is s times the Laplace transform of y minus y at t equal to 0 plus 5y. This is equal to 10 times the Laplace transform of cosine t. What is the Laplace transform of cosine t? So remember again that I told you that these are elementary things.
So s plus s upon s square plus omega square.
Very good. So L of cosine omega t is s over s square plus omega square. So this tells me that L of cosine t, where omega is just 1, is just s over s square plus 1. So plug everything in, and you use the fact that the initial conditions in this problem are such that y at t equal to 0 is 0 and y prime is 3, and you can get collecting terms with y s square plus 2s plus 5y. This is 0, so I will only have minus 3. This would be equal to 10s over s squared plus 1. Okay, so which tells me that my y is, again, the q of s in this problem is 1 over s squared plus 2s plus 5. So 3 over s squared plus 2s plus 5 plus 10s divided by, okay. So this is admittedly a little more complex than the previous problem where the Laplace transforms could be easily guessed. You could still deal with this, but to do the second part, you have to invoke partial fractions and write it in a bunch of easy fractions, right? So you have to write s over s squared plus 1 times s squared plus 2s plus 5 as some as plus b over square plus 1 and cs plus d over s squared plus s squared plus 2s plus 5. You have to figure out what a, b, c, d are, write it in easy fashions, and then figure out the inverse Laplace transform. So I will leave the rest of this as a homework. Complete this problem. Okay. So these are important problems to do because not always would you have simple functions. Sometimes you have to work hard to get it into a simple form. Okay. So any questions or any comments about this? So do you understand the general methodology for solving the problems? You take the ODE and take the Laplace transform on both sides, plug in the simple formulas for the Laplace transform of the second derivative and first derivative, get the subsidiary equation, which in this case is this, okay? And then manipulate this so that you get an equation for capital Y. What is capital Y? Capital Y is the Laplace transform of the function that you're looking for. So once you know what this is, your function itself is just the inverse Laplace transform of Y. Okay, so that is the only thing that you have to figure out. So get it into an easy form and take and guess which function is this a Laplace transform of. That is basically what the inverse Laplace transform is. So once you figure that out, you figure out the solution. Okay, that's pretty much it. Now, this admittedly are still things that you can solve using other means, right? So I can still simply say that, oh, well, I don't have to remember a whole bunch of Laplace transforms. I will use the variation of parameters or undetermined coefficients or what have you. But there are certain other classes of problems for which the technique of Laplace transform becomes even more crucial than what we have just discussed. And these are problems in which involve switching off and switching on the input. So suppose if you have a problem in which you somehow you periodically switch on and switch off an impulse, and you want to understand how the system is driven under this impulse. Okay, so how do you mathematically formulate the problem? So for example, your impulse could look like something that goes like this. Okay, so basically something that only exists for a short time and is zero and can exist again if you so wish, or just not exist at all. So this is one class of turning on and off. Another class of things that you can do is basically you just turn on and off with a sharp spike at some particular instant of time. So something like this. Okay, so these are all very rough illustrations. I'll tell you mathematically what I'm looking at. So basically your driving force is zero for every value of t, except that at some very small interval of time, at some very particular value of t, there is a very, very large spike, and that's how you're driving it, okay? So in mathematics, the first set of functions is described by what is called the step function, the Heaviside function. The second is what is called the Dirac delta function. And in problems of this sort, when you have to solve ODEs with periodic impulses like this, where switching on and off is involved, or a spike is involved, the Laplace transform technique comes into play. So equally well, you can also think of, if you have already learned them, Fourier transform techniques. If not, don't worry about it. Okay, so what do I mean? I'll first talk about the first variety. The first variety is what is called the unit step function. We will, of course, solve problems of Laplace transforms with these kinds of functions involved in ODEs. But for now, I will simply introduce what the function means, and I will stop at this point. So this is also called the Heaviside function. Okay. So what is this? So let us draw this pictorially. So I have, this is my t-axis, okay? And I have a function whose value is basically unity only after some time t equal to a. Before that, it is basically zero. So it is a constant, but the constant value is just 1, but it is a constant only after some time t. So before this time, the function is 0. After this time, the function is basically, this is 1. Okay, so this function I will call u, and this is at time t equal to a, which means that this is a convenient way to model systems in which I turn on something at some finite interval of time a. So this is called the step function because at t equal to a, there is a step, there is a unit step. And the definition of this function is as follows. Oops, excuse me. I will choose my blue definition. U of t minus a equals 0 if t is less than a and 1 if t is greater than a. Okay. Now, if a happens to be at 0, this is just u of t. Okay, so u of t is 0 for t less than 0 and 1 for t greater than 0. In general, I can turn on the impulse at any time t. Okay, the question is, what is the Laplace transform of this guy? Well, this is fairly easy. If I have to incorporate this in an ODE, I need to know how the Laplace transform acts on this function. So let us go ahead and calculate the Laplace transform of this unit step function. So this is basically integral 0 to infinity. The kernel is e to the minus st. The function itself is dt. Okay. Now remember that this unit step function is 0 for any time t, any t less than a. It only turns on at t equal to a. So below t equals a, from 0 to a, the contribution of this integral is going to be 0. So this integral is only going to be non-zero starting at t equal to a. And starting at t equal to a, the step function is just 1. So this integral is basically from a to infinity e to the minus st dt. Okay. So which is basically e to the minus as over s. So again, whenever you have functions that have to be turned on and off, or whenever you have to model like specific impulses at specific intervals of time and so on and so forth, these kinds of functions can come into play. Okay. Now there is actually another shifting theorem at play here, which is fairly easy to see. So I will talk about this shifting theorem and stop for today. So remember the first shifting theorems aside. First shifting theorem. The first shifting theorem related to the shifting of S. So this was S shifting. There is two variables, S and T. The first one was S shifting. So that basically said that if the Laplace transform of S is f of S, the Laplace transform of e to the at times f is f of s minus a. Okay, so that's pretty much it. That was the content of the first shifting. So now we will look at a second kind of a shifting theorem that will again make life simple for you, even though you have to learn one additional thing to solve problems involving step functions. That will make things very easy. The statement is as follows. So if f of t has the Laplace transform capital F of s, then the shifted function f tilde of t, which I will define as f tilde of t equals f t minus a weighted by u t minus a. In other words, this function is equal to 0 if t is less than a, and equals f of t minus a if t is greater than a. Okay, this is my definition of my shifted function. The function is shifted by an amount a, but only for t greater than a. For t less than a, the function is basically 0. Suppose if I have a function like this, then the shifted function has the Laplace transform e to the minus as times the Laplace transform of the function f of t. Okay, so if the function has the Laplace transform of capital F of s, the shifted function has the Laplace transform e to the minus s times capital F of s. Okay, so what I'm basically saying is L of f tilde, which is L of f of t minus a ut minus a, is e to the minus as f of s. Okay, so how do I see this? It's actually not very difficult to see what's going on here, because you can start either at the left-hand side or the right-hand side. So we'll start with the right-hand side. So e to the minus as capital F of s, because this quantity is known to us, this is basically e to the minus as. The Laplace transform of f of t is 0 to infinity e to the minus st f of t dt, right? And this can be written, of course, I can take this as inside, because as far as integration with respect to t is concerned, e to the minus as is a constant. So I can easily take this inside the integral and write this as, in fact, I will write this as f of tau d tau. Okay, so I'll also put a tau here because I want the t to come out at the end. So e to the minus s, sorry, what would this be? Tau plus a times s, f of tau d tau. Okay. And now we can easily see this emerging because now I'll have to write t as tau plus a. And once I do that, this quantity e to the minus as f of s is basically, there is one slight manipulation that will be involved here, because if I do this shifting from tau to t, which is tau plus a, the lower limit becomes a and not 0, right? Because when tau is 0, t is a. So we'll have to compensate for this somehow inside the integral. I'll tell you how. So this is basically minus st. This is nice because e to the minus st is the kernel that we're after. The function now is t minus a, because tau is t minus a. And of course, since a is a constant, dt is the same as d tau. Now, this is almost the Laplace transform, except for the lower limit. The lower limit is a and not 0. Okay. So in other words, I want this to be the Laplace transform of some function, but as it stands, I cannot interpret this as the Laplace transform of any function because the lower limit is all wrong. It is a and not 0. So if I have to interpret the right-hand side as a Laplace transform of a function, I can actually do a very easy manipulation and write this as 0 to infinity f of t minus a, u of t minus a dt. Why? Well, this is certainly not the Laplace transform of f of t minus a, but this can be interpreted with 0 to infinity as a Laplace transform of f times u. Why? Because between t equal to 0 and t equal to a, this integral has no contribution anyway because u is 0. So this integral only starts contributing at t equal to a. So this integral is formally the same as this integral. Okay, but now the advantage of recasting it in this form is that now I can interpret this as the Laplace transform of f of t minus a, u of t minus a. Okay, so recognize that I have not done anything bad here. I have not changed my definition of the integral. This and this are mathematically the same. All I'm saying is that instead of integrating from 0a to infinity, I'll integrate from 0 to infinity, but I'll weight the integrand by the step function. The step function will ensure that whatever I do from 0 to a doesn't really count because the step function is 0 in that range. Okay, so this basically proves our assertion that if capital F is the Laplace transform of the function f, the Laplace transform of the shifted function weighted by the step function is basically e to the minus as times the Laplace transform of the function f itself. Okay, this will come in very handy for us in many practical problems, and this is sometimes called the T shifting theorem. Okay, even if you don't regard this as a theorem, understand that how T shifting and S shifting work are actually sort of similar, but very different also. The T shifting works when I have to shift the variable with respect to the function itself is defined. And S shifting is basically if I have to evaluate the Laplace transform of a function weighted by e to the at. Okay, so the math is very simple in both the cases, but where they're applicable are two different things. So please try to solve some problems with many of these concepts. For example, the tutorial problem that we are going to upload in a short while will have lots of these problems. And if you have any questions, you can always ask me. So I'll stop recording at this point, and then if you have any questions, you can ask me.